Okay, so today we're going to be going over section 4.3 and we're going to be talking about rational functions. And so what we're going to be doing is using the techniques that we've learned in the last couple sections and applying them to the graphs of rational functions. Some of the work will be the same as what we did in pre-calculus, but we will be able to expand what we did in pre-calculus by applying the calculus to these. We're going to start with an example and walk you step by step on what I expect to see when I ask you to graph these things. So for starters, one of the points that we're usually interested in are the intercepts. There are two types of intercepts, y-intercepts and x-intercepts. As long as 0 is in the domain of your function, all functions, whether they be rational or otherwise, will have a y-intercept, and it's very easy to find. You simply substitute in 0 for x. So y-intercept, you find that by substituting in 0 for x. And you can see that when you substitute in 0 for x in this formula, you end up with 8 over negative 4, which gives you a y value of negative 2. So your y-intercept is 0, negative 2. X-intercepts are a little bit more challenging. Same kind of thing. You're now being asked to find where the y value is 0, because you're crossing the x axes, so your y value has to be 0. But for rational functions, when you substitute in 0 for y, then you are trying to make a fraction equal to 0. And the only way that you can make a fraction equal to 0 is if the numerator is 0. And since the numerator in this problem is always 8, there is no x-intercept. So no x-intercepts. Moving on, we want to talk about asymptotes. Now, in pre-calculus we talked about asymptotes, and so we could do this problem in pre-calculus. We would just do it a little bit differently than what we're doing now. Now we want to use the calculus. But next, let's move on to finding the asymptotes. So again, there are two types of asymptotes. There are vertical asymptotes and horizontal asymptotes. So to find the vertical asymptotes for rational functions, those happen at numbers that make the denominator 0 and not the numerator. So since the numerator is always 8, in this problem we don't have that. We don't have to worry about that. So we just figure out what makes the denominator 0. X squared minus 4 equals 0. So then x squared would have to equal 4. So then x will have to equal plus or minus 2. And so for the, these are the vertical asymptotes. So for the horizontal asymptotes, we're wondering what, if anything, does the y value go to as we move further and further to the right? If we level off to a number, that's a horizontal asymptote. So what I expect to see is the limit as x goes to infinity of 8 over x squared minus 4. Now the top is staying fixed at 8, and x is increasing without bound. So when you square it, that increases without bound. Subtract 4, it's still increasing without bound. And so this limit is 0. And so then your horizontal asymptote is a horizontal line, and it is the horizontal line y equals 0. Very common misconception for people to believe that a graph cannot cross its asymptotes. And for a rational function, it is true that a graph cannot cross its vertical asymptotes, right? Because vertical asymptotes happen at where the denominator is 0. So you can't cross a vertical asymptote if when you plug that number in, it makes your denominator 0. But you can cross a horizontal asymptote, right? So let's work on that next to figure out where the graph crosses the horizontal asymptote. Okay, so we figured out in the last slide that the horizontal asymptote is y equals 0. So to figure out where the output is 0, we just substitute in 0 in for the output, and you get 0 equals 8 over x squared minus 4. Because the horizontal asymptote is the x-axis, and we've already decided this does not have any x-intercepts, then this graph does not cross the horizontal asymptote. So the graph does not cross. Horizontal asymptote. Next comes the calculus. We want to look at the sine graph or the sine chart for f prime. The f prime, the first derivative of the function, tells us where our function is increasing or it's decreasing, and so that's important to us. So we're going to look at the sine chart for f prime. Okay, so to look for the sine chart for f prime, first thing we have to do is figure out f prime. This is a quotient, so we should use the quotient rule, and then f prime of x will simply be the derivative of the top, 0, times the bottom left alone, which is still 0, minus, leave the top alone, 8, times the derivative of the bottom. But the derivative of the bottom is 2x, so you get minus 16x. All divided by x squared minus 4 squared. Okay. Now, because the x squared minus 4 is being squared, what you should tell is the denominator is never negative, right? It is undefined. It's undefined at 2 and negative 2. That's what makes it 0. We didn't get any new zeros because we just squared the bottom. And so, but this square here makes it so that the denominator is always positive. But the numerator is negative 16x. So when I go to look at my sine chart for f prime, the only number that belongs on there is 0, because that is the only number that makes the numerator 0. And to the left of 0, if you plug in negative 1, negative 2, or so on, you're going to get a positive output. Negative times a negative will be a positive. To the right of 0, a negative times a positive will be a negative. And so again, we also should include on my sine chart all the critical numbers. The critical numbers are the numbers that make the derivative 0 or undefined. I only have what makes it 0, but undefined is over here at negative 2 and 2. But again, notice that my sine chart doesn't change at negative 2 or 2 because the denominator is being squared. So we have two types of critical numbers. We have numbers that make the derivative 0. Those are called stationary points. We have a stationary point right here at 0. And we have numbers that make the derivative undefined. That's at negative 2 and 2. Next, we want to find any stationary points. We've already said that we have a stationary point at 0, which means at 0, negative 2, which is the y-intercept, we have a stationary point. So now we want to look at the sine chart for the second derivative. The second derivative tells us when our function is concave up and when it's concave down. Positive second derivatives means that our original graph is concave up. Negative second derivatives tell us that our original function is concave down. So we need to look at that. So again, finding the second derivative, we're going to start where we left off. The first derivative was negative 16x over x squared minus 4 squared. And rather than expanding the bottom, we'll show you a little trick that's going to help us here. We're going to find the second derivative by leaving the formula as it stands. And then we're still going to use the quotient rule because we still have a quotient. The derivative of the top is negative 16. The bottom gets left alone. X squared minus 4 squared. And then minus, but with that negative 16 as my first factor, it was going to be plus 16x times the derivative of the bottom, the x squared minus 4 squared. Now this is a composition, and so then we'll bring down the exponent, 2, take 1 away from the exponent, but the base stays the same, x squared minus 4. And then we multiply by the derivative of the inside. What's inside the exponent of 2 is this x squared minus 4, and so then that is 2x. Now, the trick is that because we have this x squared minus 4 squared, we're going to have x squared minus 4 here and x squared minus 4 here, and we'll be able to factor that out, and we'll do that in just a moment. But don't forget that your denominator is x squared minus 4 squared. This is going to actually make the algebra just a little bit easier. So if you look, here is your plus, and in this term right here, you have an x squared minus 4, and you have a 16. Over here, you have a 16 and an x squared minus 4. So then we can pull that out into the front and get 16 x squared minus 4. And so from this term, we took out the 16, took out the x squared minus 4. What's left is the minus and one of the x squared minus 4s, since we had two of them. So we end up with minus x squared plus 4. And then over here, we took out the 16. We took out the x squared minus 4. So what's left is a 2x and a 2x plus 4x squared. And then in the denominator, we still have the x squared minus 4. And I've just noticed a mistake. Hopefully you caught it as well. That 2 should be a 4. So let me go ahead and get rid of that. When we squared the bottom, we got x squared minus 4. It should be to the 4th because you multiply the exponents. So here you get x squared minus 4 to the 4th. Okay, but now one of these will go away, and this 4 will now become a 3. And then what this becomes is we have a 16, and then the minus x squared and the plus 4x squared is 3x squared, and then plus 4. And in the denominator, we have x squared minus 4 to the 3rd power. Now, because this is an odd power, right, not an even power like it was for our first derivative, that the bottom is sometimes positive, sometimes negative, depending on whether the base is positive or negative. And so then what we should do is we should write it in factored form. And so this is x plus 2 times x minus 2. That's the x squared minus 4, but you were raising it to the 3rd power, so you have an odd number of both of those as well. And now we're ready to make the sign chart for the second derivative. And the only numbers, the numerator now is always positive. If you look at the numerator, it's 3x squared, that's positive, plus 4. Right? So the numerator is always positive. We just have to look at the denominator. So the only numbers that are where my graph will change signs are over here at -2 and over here at +2. To the left of -2, they are both negative numbers. And when you multiply them together, you will get a positive number. Once you get past -2, this one will switch. And now a positive times a negative will be a negative. And once you get past 2, this one will switch. And now a positive times a positive is a positive. The odds don't change anything. Because this is odd, rather than having a single negative, you would have 3 negatives, which is still negative. And same thing goes on over here. So this is the sign chart for f double prime. This tells us that our graph is concave up to the left of -2, concave down in the middle, and concave up to the right of +2. We do not have an inflection point at -2 because we don't have a point at -2. -2 is not in the domain of my function. And so we don't have. So another point of interest that we were not able to find in pre-calculus are the points of inflection. So this says for the function find any inflection points. But again, if we go back and look at the sign chart, and there's my sign chart. If we go back and look at the sign chart, the only place where this graph changes concavity is at -2 and 2. And those points, there is no point at -2 or +2. Those points are not in the domain of my function. So there aren't any inflection points. Use the information to make the graph of f. Now we want to make the graph, right? So we're just going to make a quick sketch. We automatically know that our graph has a y-intercept at 0, -2, so we should put that there. We know that we have a vertical asymptote at x equals plus and minus 2, so draw a vertical line there. And again, what a vertical asymptote tells you is that as your input approaches an x value of 2 or -2, we should label them x equals -2, x equals +2. Your output takes off to either positive infinity or negative infinity. Okay, and then we know that the horizontal asymptote is y equals 0, which is just the x-axis. I'll just draw it right above the x-axis. And what that tells you is that as you move further and further to the right, your graph gets closer and closer to this horizontal line. Okay, so now we can use that information to make our graph. So we'll start on the left over here. Our graph is increasing from -infinity to 0, and since it's increasing over here on the left, since it's increasing, and as we get closer to -2, we need to take off to either negative infinity or positive infinity. We can't take off to negative infinity because that would be a decreasing function, right? So, and we also saw that it never crossed the x-axis. So if we start here, then we have to be going up because this is an asymptote, and we have to be increasing. So starting here, as we go to the left, we have to level off to a y value of 0, and so then we get flat. Okay. Now, I continue to increase until I get to 0, and then at once I get past 0, I start to decrease. So that means at this point right here, this is a relative max, right? It's obviously not an absolute max because you have these points over here that are higher. But my graph needs to be increasing, and as we come over here, we have to be going off to negative infinity. Once we get past 0, we start decreasing, and then my graph is always decreasing. And so then we have to be going down like this. Also, I forgot to mention the concavity, right? So over here, we have to be increasing and concave up. Over here, we have to be increasing and concave down. In between -2 and 2, we're concave down. So this has to bend downward so that my tangent lines lie above. Over here, my tangent lines lie below. Okay, now to the right of 2, we're decreasing and concave up. So again, we have to be taking off to either positive or negative infinity as we're getting closer and closer to 2. And because we're decreasing, we cannot be taking off to negative infinity. That would make us increasing. So we're above the x-axis. We have to be taking off to positive infinity and something like that. And then as we go in the other direction, we get there. That's what the graph should look like. We'll look at another example, again, step by step. You might want to pause the video and try and do this problem on your own, and then compare your work to what is on the video. But again, we begin with the same, we want to find the intercepts, right? So again, y-intercept is very simple. put 0 in for x. And when you put 0 in for x, this term and this term go away. You get 0 over negative 4, which is 0. So in this case, your y-intercept is the same as your x-intercept. This point is both on the x and y-axis. So for the x-intercept, you're trying to figure out what makes the numerator 0, and the only thing that's going to make the numerator 0 is 0. So in this case, your x-intercept and your y-intercept are the same, right? So x-intercept, you're trying to make the whole thing 0, and the only way a fraction can be 0, a single fraction can be 0, is if the numerator is 0. So moving on, we can look for the asymptotes. Okay, so now we're trying to find the asymptotes of this function. And so again, vertical asymptotes we find simply by figuring out the zeros of the denominator. So x squared minus 4 equals 0. So then x squared equals 4. So then x is equal to plus or minus 2. Horizontal asymptotes. We figure out what is happening to the expression as x gets bigger and bigger. So we take the limit as x goes off to infinity of x squared over x squared minus 4. If you remember your results from last semester, you can use that. If we multiply the numerator and denominator by 1 over x squared, 1 over the largest power in the denominator, then we rewrite the expression in a form that makes it easier to see what's going on as x increases without bound. And so what we get is 1 over 1 minus 4 over x squared. And you see then that this allows us to see that this term right here goes to 0. And so then the other terms stay at 1, and your answer is 1. So your horizontal asymptote is y equals 1. Okay, so next we want to see where the graph crosses the asymptotes. And so again, can't cross the vertical asymptotes because they happen where the function is undefined. So we just want to see where it crosses the horizontal asymptote. So we put 0 in for the output because we put 1 in for the output. So we're putting in 1 for the output, so 1 is equal to, so we want to know where this crosses the line y equals 1. And so then if we multiply both sides by x squared minus 4, we get x squared minus 4 is equal to x squared. We then see that if we subtract x squared from both sides, we get negative 4 equals 0, which is not true. So that tells us that in this case, again, the graph does not cross the horizontal asymptote. But it is possible for the graph to cross the horizontal asymptote. It just doesn't in this case. Next, we want to see, look at the sign chart for the first derivative. And so to look at the sign chart for the first derivative, we first have to figure out what the first derivative is. So again, quotient rule, derivative of the top, 2x, bottom left alone, x squared minus 4. Take the minus, leave the x squared alone. Take the derivative of the bottom, 2x. And then on the bottom, we get the bottom squared. Very difficult to see what the sign chart looks like by the way the expression is written. Notice that we have a 2x here and a 2x here, so we can factor out a 2x rather than distributing in here. We can factor out the 2x. What that leaves behind is x squared minus 4 minus x squared, and then x squared minus 4 squared. The x squareds will go away, and then we will get minus 8x over x squared minus 4 squared. Again, our critical points are numbers that make the derivative 0 or undefined. The derivative is undefined at plus or minus 2. And it's only 0 at 0. The only way to get a fraction to be 0 is if the numerator is 0. And again, because the denominator is being squared, the denominator is always positive, so the sign of the derivative is solely determined by the numerator. And again, negative 8x is a line that is decreasing, so to the left of 0, it's going to be a positive number. And once we get past 0, then it's a negative number. Okay, so again, the stationary points are where the derivative is 0, and there's only one stationary point that's at 0. If we look at the sign chart for the first derivative, to the left of 0 it's increasing, to the right of 0 it's decreasing, so at 0 we have a relative maximum, but it is a stationary point. We have negative 2 and 2 on our sign chart, but those are where the derivative is undefined. Those are not stationary points. So next we want to look at the sign chart for the second derivative. The second derivative tells us where the function is concave up and concave down. So next we have to look at that. And so again, I encourage you to pause the video and try things on your own and then follow along with the video, rather than just sitting here listening to me talk. Our first derivative was our first derivative was negative 8x over x squared minus 4 squared. And to find the second derivative, we're going to use the same trick. We're not going to expand the denominator, and that'll make things a little bit more challenging, more tedious. And so instead, we're just going to go ahead and use the quotient rule and the chain rule. Derivative at the top, negative 8, bottom left alone, x squared minus 4 squared, plus, because of the minus 8x, that's going to make the minus in the quotient rule a plus 8x, the derivative of the second one. But the derivative of the second one is a composition. I'm sorry, the derivative of the denominator is a composition. Bring down the exponent, 2. Take 1 away from the exponent, 1. Same inside, x squared minus 4 times the derivative of the inside, 2x. And then we get the denominator squared, x squared minus 4, now to the 4th power. Okay. Again, same trick. If you look here, the x squared minus 4 and the x squared minus 4 are in both terms. The 8 and the 8 are in both terms. So we're going to go ahead and factor that out. We're not going to factor out the negative. Okay. So when I factor that out, it's going to cancel out with one of these x squared minus 4 is this down here. And so then, let me not skip that step. So we're going to factor out the x squared minus 4. And what's going to stay behind is, I'm sorry, we're also going to take out the 8 since they both have an 8. And then what that's going to leave behind is the negative in front of the x squared minus 4, which will make minus x squared plus 4. And from this, we'll have left 4x squared. So from this term, negative x squared plus 4 plus And then we took out the 8 and the x squared minus 4, 2x times 2x, 4x squared. And on the bottom, we have x squared minus 4 to the 4th power. Now, we're going to get rid of one of the x squared minus 4's on the bottom. And so then we will end up with x squared minus 4 to the 3rd power. And again, since we're going to make the sign chart for this, it's going to be better if we factor this. And so then rewrite it as x plus 2 to the 3rd power, x minus 2 to the 3rd power. Right? And one of the x squared minus 4 went away. Here, the minus x squared and the plus 4x squared make 3x squared. The 8 is still there. And we get 3x squared. And then plus 4. Notice again that the numerator is always positive. And the denominator could be positive or negative depending on what we have for x, because we have these odd exponents. So odd exponents have both positive and negative outputs. But the only numbers that make the derivative undefined, nothing makes the derivative 0, the second derivative 0, I should say, are negative 2 and 2. And same thing is going to happen again when you put in numbers less than 2, this expression will be negative. This expression will be negative, multiply it together, and we will get positive. Once we get past negative 2, this one switches to being a negative number. To being a positive number. Cubed is a positive number, and this is still a negative number, so a positive times a negative is a negative. Once we get past 2, this expression here will become a positive number. This one was already a positive number, and so we have positives. And this is the sign chart for the second derivative. It tells us that our graph is concave up. Over here it's concave down, and then over here it's concave up. So again, we want to find any inflection points. We look at the sign chart for the second derivative and to look for inflection points. But you can see that the only place it changes concavity is at negative 2 and 2, but there is no point at negative 2 or at positive 2. So the graph does not have any inflection points. And now we can take all this information and make a graph of f. And we have the point 0, 0 on our graph, the only point that we're going to use. We have vertical asymptotes at x equals negative 2 and x equals positive 2. Okay. The only place the graph crosses the x-axis is right here. It never crosses it again. We have a horizontal asymptote, of y equals 1. And we never cross the horizontal asymptote, right? So to the left of negative 2, the graph is increasing and concave up. And as we get closer to negative 2, as we have to take off to positive infinity, and since we never cross the horizontal asymptote, since we're increasing, we have to take off to positive infinity. Can't take off to negative infinity on this side. And since we never crossed the horizontal asymptote, we have to have started above the horizontal asymptote and then go up towards positive infinity. And the horizontal asymptote means that as we take off to the left, my y values get closer and closer to a y value of 1. In this case, it never touches 1. To the right of negative 2, right? So we're still increasing, but now we're concave down, right? So now my graph is bending down. And so we're increasing in concave down, and this is an asymptote. So we can't be up here. We got to be down here because we're increasing. and we got to connect with this point, and we got to be concave down. Once we get past 0, we start to decrease, and then we are concave down some more. Something like that. And then once we get past 2, we start to decrease still. I'm sorry, we continue to decrease, but we're concave up. We're bending upwards. So decreasing means that as we come in this direction, we have to go up towards positive infinity so that we can be decreasing on our way back down. We never crossed the horizontal asymptote, so we can't be below it. So we have to be up here. And so then going up towards positive infinity. And as we come down, then we have to be going towards y equals 1. And so there's your graph. So now we're going to look at a different type of function. This is not a rational function. We did not go over these types of graphs in pre-calculus. We don't want to just plot points, have no idea what this thing is going to look like. And so instead we're going to use our calculus on it and some algebra as well. For the function f of x equals the cube root of x squared minus 4, find the intercepts. Okay. So again, y-intercept, we substitute in 0 for x. Need to be careful. As soon as people see roots, they think, oh, you can't root a negative number. You can't square root a negative number and get a real number, but this is an odd root. So perfectly fine to put in 0, and we end up with the cube root of negative 4, which does not have a nice answer, but it is a negative number. So we cross the y-axis below the x-axis. X-intercept. We just set the output equal to 0, so 0 is equal to the cube root of x squared minus 4. And then we can work backwards. There's x, we're squaring it, subtracting 4, and then we're taking the cube root. So first we undo the cube root. We undo the cube root by cubing it. And this will give us 0 is equal to x squared minus 4. Then we can add 4. And then x is equal to plus or minus 2. So we have y-intercept of 0, cube root of negative 4, and x equals plus or minus 2. Next, we might ask, does this have any asymptotes? So the domain of this function is all real numbers. Asymptotes happen at places where your function is undefined, and so this does not have any asymptotes. Now we can look for the sign chart for f prime of x. Then let's look at what the derivative is. Let's analyze the derivative and see what that tells us about the graph. Okay, so again, this is a composition. To better see that, we can rewrite this as x squared minus 4 to the 1/3 power. And you are taking the x squared minus 4 and substituting that into the 1/3 power function. So this is a composition. So to find the derivative, we use the chain rule. We bring down the exponent, 1/3, same base, x squared minus 4. Take one away from the exponent, negative 2/3 times the derivative of the inside, 2x. Again, anywhere along the video, you should stop and see, can I find this by myself, and then check my answer, check your answer with what I'm doing. Okay. Okay, so we have the derivative of this function, 1/3 times x squared minus 4 to the negative 2/3 times 2x. Now, again, what this negative tells me is that these factors actually belong in the denominator. So we will go ahead and write a fraction. In the denominator, we already have the 3. The 2x is in the numerator. And the x squared minus 4, those factors of x squared minus 4 belong in the denominator. And the 3 in this exponent, and this 3 right here, is telling me that we're taking the cube root. And so then we have the cube root. And the 2 is telling us that we are squaring this. And so there's what our derivative looks like in this form. Actually, we can do one more thing to make things a little bit more obvious, that this is equal to 2x3 cube root, and x squared minus 4 factors is x plus 2 squared, and then x minus 2 squared. And so now we are ready to make the sign chart, right? And so for the sign chart, for our derivative function, the critical numbers are the numbers that make the derivative 0 or undefined. And so then they will be made 0 at 0, and they will be made undefined at -2 and 2. And those numbers come from this right here. I had to give myself some more room, and I should be ready to go now. Okay, so now we're ready to make the sign chart for the first derivative. And this is where the first derivative is either undefined or 0. 0 is found by what makes the numerator 0, and the only thing that's going to make that 0 is 0. Undefined is what makes the denominator 0, and we have -2 and 2. And again, because of these squares, the only thing that determines whether my output is going to be positive or negative is the numerator. 2 times x to the left of 0 is going to be negative. And so again, to the right of 0, your derivative is going to be positive. Again, -2 makes the denominator 0, and although -2 is in the domain of our original function, it's not in the domain of the denominator. But this tells us that because the -2 makes the denominator 0 and not the numerator, that means this function here, the derivative, has a vertical asymptote at -2. That means that as we approach this x value of -2, your tangent line has a slope that is decreasing without bound, so it's getting more and more vertical. Likewise, the same thing happens over here at +2. +2 makes the denominator 0, but not the numerator, so this function, the derivative function, has a vertical asymptote, which then tells us that the slope of the tangent line is increasing without bound there, which then means that your tangent lines are getting more and more vertical. So then what we are expecting to see at -2 and at 2 is a cusp. Okay, so again, the stationary points are where the derivative is 0. When we looked at the sign chart at -2 and 2, the derivative was undefined. So those are not stationary points. The stationary point is when x is 0. Next, we want to look at the sign chart for the second derivative. That will tell us where our function is concave up and concave down. So again, f prime of x was 1/3 x squared minus 4 to the negative 2/3 times the derivative of the inside was 2x. And so then if we write this as 2x over 3 times x squared minus 4 raised to the negative 2/3, but we can find the second derivative by looking at the product rule, by using the product rule, because now we have it as a product and we don't have to use the quotient rule. Not that big a deal, but okay, so there's a nice little trick here that I'm going to show you. So the derivative of 2x divided by 3 is, that's just no need for the quotient rule or anything. It's just 2/3 times x. The derivative of x is 1. So the derivative of 2/3 x is just 2/3. And so then the second factor gets left alone, x squared minus 4 raised to the negative 2/3. And then plus, and then we leave the 2/3 x alone, and we take the derivative of this piece. But this piece right here is a composition, power function. Inside the power function we have x squared minus 4. So we're going to bring down the exponent, and we'll get a negative 2/3. And then we will take one away from the exponent, and negative 2/3 minus 1 is negative 5/3. Okay, and then inside here we get x squared minus 4, same inside, and then we multiply by the derivative of the inside, 2x. So my second derivative then is 2/3 times x squared minus 4 plus 2/3 x. I'm sorry, let me pause this for a moment. So when we clean this up, we have this minus here, and the 2/3 times the 2/3 is going to be minus 4/3 times this other 2 is going to be minus 8/3. So again, that was the 2/3 times the minus 2/3 times the 2. So that would give us minus 8/3. We'll multiply straight across. And then we have the x times the x, and that will give us x squared. And then we have this other factor of x squared minus 4 to the negative 5/3. But I forgot my exponent here, the 2/3, this was x to the negative 2/3, so let me go ahead and fix that. Now we're going to do something that's a little different than what you may have done in your algebra classes. You can see that there is a common base or a common factor, and to be consistent with what you did with in your other classes, you would always factor out the greatest common factor, which would be the smallest exponent that was common to both of them. And so then smallest here would be this negative 5/3. And so we are going to factor out the x squared minus 4 to the negative 5/3. So the way I like to factor things out is by asking myself, if I were to back distribute, what would need to be here so that I would end up with what I started with, right? And so then I could have taken out the 2/3 as well, so let me go ahead and do that. So again, what I ask myself is what needs to be here so that when I back distribute all this, I end up here. Okay, so I don't need the 2/3 because I'm bringing in the 2/3. I have an x squared minus 4 to the negative 2/3, so it probably has a base of x squared minus 4, and I have to figure out the right exponent. But when I multiply, I add the exponents. So then, in order to end up with a negative 2/3, the exponent that is here needs to add with negative 5/3 to give me negative 2/3. And so then that is going to be positive 3/3 or 1. So I end up with an exponent of 1, which I don't have to write. Minus, I pulled out the 2/3, so then that would just be 4. And then that way the 2/3 times the 4 would give me the 8/3. And then I pulled all of this out because it's over here. And so then what's left is just the x squared. And then now we don't need this parenthesis here. Okay. So let's clean this up a little bit. 2/3 x squared minus 4 to the negative 5/3, and then the x squared minus the 4x squared is minus 3x squared minus 4. And now you can see, now let's go ahead and rewrite this as we'll keep this 2 in the numerator and distribute it. And we will get negative 6x squared minus 8. And then this is a negative exponent here, so that tells us that this belongs on the bottom with this 3. And 3. And then the denominator of 3 tells me that we have a cube root. And the exponent of 5 tells us that we're raising x squared minus 4 to the 5th power. But x squared minus 4 factors as x plus 2, x minus 2, and it's being raised, both of them are being raised to the 5th power. This is my second derivative. So to make the sign chart for the second derivative, we only put on there the numbers that make the denominator 0 or undefined. Notice that x squared is positive, so when you multiply it by negative 6, it's negative, and when you subtract 8, it's still negative. So the top here is always negative. It never changes, right? In the denominator, because we have odd powers, those will change, right? So over here at negative 2 and positive 2 are where my numbers that make the second derivative undefined. There's no place where that makes the second derivative 0. To the left of negative 2, negative 3, negative 4, both of these will be negative. Raised to the 5th power is still negative, so you're going to get a negative times a negative is a positive, but then you still have this negative up on top, and so you end up with a negative. Don't forget that. And remember what that tells you is that your graph is concave down. Once you get past negative 2, then this one switches, and then when you put in 0, negative 1, 1, this will be a positive number. Raised to the 5th power will still be a positive number times this negative number. This one hasn't switched yet, so you'll end up with a negative number, but you have a negative in the numerator, and so then you will get a positive. Once you get past 2, then this one now switches again. They never switch back, and this one stays always negative, and so now you only have that lonely negative up on top, and so this becomes negative. And so this is your sign chart for the second derivative.
Are you off recording? We got an Fresno County is recommending shelter in place as of noon today.
Okay, so now we're going to find any inflection points, and points of inflection are points where the graph changes concavity. And so if we look at the sign chart for the second derivative, we see that to the left of -2, the graph is concave down, and then in between -2 and 2 the graph is concave up, and then past +2 the graph is concave down. So -2 and 2 are not in the domain of the derivative, but they are in the domain of the original function, and so there you do have an inflection point. It is a point of inflection. Okay, so now we're going to use all that to make the graph of f, right? So we're going to need a surprisingly few number of points. We already have the y-intercept, 0, cube root of -4, which is cube root of -4 is going to be a small value. We have intercepts at 2, 0, and -2, 0. Okay, and to the left of 0, it's a decreasing function, and from -infinity to -2, it's decreasing and concave down. So it'll be doing something like this. And then once we get past -2, it's still decreasing, but then it's concave up. And it connects to this point over here, so it looks something like this. Again, the slope of the tangent line there is going to be vertical as we're coming in from the left and from the right, because there was a vertical asymptote for the derivative function. Once we get past 0, we start increasing and also stay concave up until we get to 2, so until we connect to this point over here. And then once we get past that point, then we are again increasing, but now concave down. And so you have a graph that looks like this. Next, we'll turn our attention to a trig function. We didn't graph anything this complicated back in trigonometry. F of x equals the sine of x plus the cosine of x. Now, since both the sine function and the cosine function are periodic of period 2 pi, it should make sense that this function be periodic of at least of at most period 2 pi. Something might happen to shut down close down the period, but it won't be any more than 2 pi. So we'll only focus on this function on the interval from 0 to 2 pi. Okay, so now we're going to find the intercepts. And so first, always easiest, y-intercept. And again, for the y-intercept, we substitute in 0 for x, and the sine of 0 is 0, and the cosine of 0 is 1. So we have the point 0, 1 is my y-intercept. For my x-intercept, we let y be 0. And when you see a trig function with two variables like this, with two trig functions like this, it's kind of like having an equation with two variables. So if we could do something to make it so that we only had one trig function, then life would be a little easier. So we could subtract the sine of x from both sides. And then we could divide both sides by the cosine of x. And then the usefulness of that is that the sine of x over the cosine of x can be divided, it can be seen as the tangent of x. So you get negative tangent of x is equal to 1, or the tangent of x is equal to negative 1. Okay, so again, we're only interested in the interval from 0 to 2 pi. So then we're looking in quadrants A, S, T, C. We're looking for the tangent to be negative, and so that's either in quadrant 2 or in quadrant 4. The ratio of 1 comes from pi over 4, so your reference angle is pi over 4. Okay, and so that means that your angle from here to here is 3 pi over 4, 1/4 away from 1, and then this one over here is 7 pi over 4, 1/4 away from 2. So your x-intercepts happen at 3 pi over 4, comma 0, and 7 pi over 4, comma 0. And next we're being asked to find the asymptotes, but you should know that the sine function is continuous everywhere, and that the cosine function is continuous everywhere, so there are no asymptotes, and then when you add the two together you get a continuous function. So the domain of this function is all real numbers, and it's not there are no asymptotes. So we move on to find the sine graph for f prime of x. And so for f prime of x, we need the derivative, but the derivative is not very difficult to find. The derivative of the sine function is the cosine function, and the derivative of the cosine function is the negative sine function. And so then the sine graph for this, we need to figure out what makes this 0. And so then we again can't tell just by looking at this by inspection, so we find the zeros of this, and because this is a continuous function, everywhere in between the zeros it will always be positive or always be negative. So then again here we could do the same trick. We can add the sine function to both sides, divide by the cosine of x to get the tangent of x. And so now you're looking in quadrants 1 and 4, and the same reference angle, pi over 4. And so then your angle is pi over 4, and 4 pi over 4, 5 pi over 4, quarter more than 1, 5 pi over 4. So now in the interval from 0 to 2 pi, your only critical numbers are pi over 4 and 5 pi over 4. Okay, so you have to find something in between 0 and pi over 4, or 0 and 45 degrees. So we could use 30 degrees. And again, 30 degrees, 30, 60, 90 triangle, where this is 60 degrees, and this is 30 degrees, this is 1, this is 2, and this is the square root of 3. And the derivative is, so then f prime of 30 degrees, or pi over 3, makes no difference, those are just names. The cosine of 30 degrees is root 3 over 2 minus the sine of 30 degrees, 1/2, and root 3 over 2, since root 3 is more than 1, root 3 over 2 is more than 1/2, and so then this is going to be bigger than 0. So then it's positive here. Past pi over 4, in between 5 pi over 4, we can use pi over 2 because that has a nice output, a quadrant angle. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. 0 minus 1 is negative 1, and that works out like that. Now we need to get past 5 pi over 4, and we can use 3 pi over 2. That's another quadrant angle. Cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is negative 1, so minus the negative 1 gives us a positive 1. And so we're going to be positive. And so then we have two critical numbers. We have pi over 4 and 5 pi over 4. Both of them are stationary points because both of these numbers have a derivative of 0. So the stationary points happen at pi over 4 and 5 pi over 4. And so we should keep track of those as well. Lots of functions floating around, but again, we're interested in the graph of f of x, and f of x is the sine of x plus the cosine of x. And so then the sine of pi over 4 is root 2 over 2, and the cosine of pi over 4 is root 2 over 2. And so then when you add those together, you get root 2. At 5 pi over 4, the sine is negative root 2 over 2, and the cosine is negative root 2 over 2. So when you add those together, you get negative root 2. For the function f of x equals the sine of x plus the cosine of x, find the sine graph for f double prime. So we need the second derivative. We already know what the first derivative is, the cosine of x minus the sine of x, so we just take the derivative of this and we get negative sine of x minus the cosine of x. Right? And so again, we need to figure out the sign chart for this, and so we need to figure out what makes it 0. So then 0 is equal to negative sine of x minus cosine of x. Same trick, add the sine of x over. Sine of x equals negative cosine of x. Get rid of the, divide both sides by the cosine of x so that we end up with the tangent of x equals negative 1. And so then x is equal to, so we're looking again for negative tangent values of 1, and we've already done this, it's the same thing. These happen at 3 pi over 4 and 7 pi over 4. But the sign chart for this is going to look different. And so then the only numbers that go on here are going from 0, then 3 pi over 4, 7 pi over 4, and 2 pi, not to scale. Okay. So again, we're looking for what the output is for these in these intervals. We have a continuous function. These are the only zeros. So in each interval, the output is either always positive or always negative. It's not obvious what it is. So again, we could use a 30-degree angle, actually no, at 3 pi over 4, we could use pi over 2. And at pi over 2, this one's 0, and this one is 1, so we'll get negative 1. So we get negative. Use a number in between 3 pi over 4 and 7 pi over 4. We could use pi, and so the cosine of pi is negative 1, with the negative makes it positive 1, and this one is 0. So at pi it's positive, so everywhere in the middle is positive. Between 7 pi over 4 and 2 pi, you could use 300 and, you could use 300 degrees because this is 315 degrees. This is 315 degrees, so you could use 330 degrees. And for 330 degrees, the reference angle is 30 degrees, and the cosine is positive. Again, the 30, 60, 90 triangle and so then you get the square root of 3 over 2, and then the sine of 330 degrees again is going to be negative now because you're in this quadrant, and 30 degrees 1/2. But your second derivative is the negative sine of x, so that'll be a positive 1/2 minus the square root of 3 over 2, and so then the square root of 3 over 2 is more than 1/2, so that will give us a negative output. And so we have inflection points at 3 pi over 4 and 7 pi over 4, and those happen to be our intercepts, I believe. Yep. Okay. So those, we have the inflection points at 3 pi over 4 and 7 pi over 4. And we already have those on the table, so we're ready to go. So now we can make the graph, right? So to make the graph, we should have our sign charts on there. Okay, so we are ready to graph this thing now that I have my sign charts up. The graph has a y-intercept at 0, 2. We have x-intercepts at 3 pi over 4 and 7 pi over 4. Okay. From 0 to pi over 4, the graph is increasing. And it increases to a maximum, relative maximum of the square root of 2. And it does that in a concave down fashion. So connect this with a nice concave down curve. Okay. Once you get past pi over 4, you start decreasing, and you continue to decrease until you get to 3 pi over 4. At 3 pi over 4, you also you are at 0, and you're still concave down. Once you get past 3 pi over 4, you're still decreasing, but now you are concave up until you get to 7 pi over 4. Okay, so at 7 pi over 4, we're back at 0. But from 0 to pi over 4, from 3 pi over 4 to 5 pi over 4, we're decreasing. At 5 pi over 4, we're at negative the square root of 2. And we are decreasing and concave up. So we should connect this with the decreasing concave up curve. There we go. And then once we get past 5 pi over 4, we start to increasing, and we're still concave up until we get to 7 pi over 4. And then once we get to, we continue that until we get to 2 pi. And at 2 pi, we're going to be right back where we started. At 2 pi, we're going to be back at 1. And so then we're increasing and concave down. And if you just continue that curve, that's what the curve will look like. And so here's your homework for this section. We'll continue tomorrow.